Alright, welcome. Probably next last full week of class if I had to guess, so I think we'll have both meetings this week, both meetings next week, and then the fourth project is due at the end of next week, and then we'll have our last meeting with the final sort of lab on Tuesday, May 26th. That's probably all we're going to need of finals week, but remember during finals week we're meeting at the normal time. Okay, so we're still working on the binary search tree, which is the data structure that will be exercised in Project 4. I'm going to do a little bit of playing around with some Project 4 setup today after I do a little bit of the binary search tree for the lab. We're on lab 15 this week. Um, to just draw your attention to some things that you can do. So the main problem I think I saw in Project 3 was that you hadn't really exercised your code very much. So there was a sample input file, and probably some people realized it, but not everyone realized it, that a sample input file means that it's a sample of an input file, which means there's probably other input files. But it turns out that um, you can make your own input files and use them to target functionality in your data structure. And you can be testing your driver at the same time. So the input file is just a text file, which means that you can make it be whatever you want. So um, I'll show you an example of that, and maybe it's that some of you waited till the last second. You didn't really have time um, to do that extra work, but it's a thing that you want to get in the habit of, is giving yourself time to test your implementation before uh, you send it out into the world. Unless you work for Microsoft, then you can send whatever crap you want to out into the world. Uh, and they pay well. But in school, at least, most teachers are going to hold you to a higher standard than buggy software if we can help it. So I'll give you some ideas about that after we do a little bit of the binary search tree. Um, but you do need to leave yourself, or at least that's the idea, is you need to leave yourself some time. So we've only got 2 weeks at this point on the last project. So try to leave yourself some time to do some testing. I don't think the Discord channel is used much in this class, but the Discord channel is there for you to reach out and seek help and to offer help and to interact with each other. So these are solo projects, but that doesn't mean that you can't talk to each other and share testing files. Like, hey, I made a sample input file of my own. Does anyone want to share one that they made, and we'll swap ideas. So I'll try to encourage that after we get through some of the lab work today. So you want to finish strong, and looks like we have a small audience today, but you want to finish strong if you can, so that you go into whatever comes next with some confidence. And the only way to do that is to put in the hours, unfortunately, to make it happen. I've set up this little driver just so I can show you that after we do some binary search tree. I think I have not. Let me get my camera running real quick so I could draw pictures if I want. Okay, if I need it, I will draw pictures. I'm going to re-implement everything. You don't have to do that. This lab, just like we did in the last cycle, this lab builds on the prior lab, so you can really just take the code that was completed in the last lab and add it to this. But I'm going to rewrite the whole thing just to reinforce some points, although I'm going to do it faster. So the constructor needs to make sure that the fields of the tree, and for the tree, that's the size, should be 0, and the root should be null. So that's all the constructor has to do. And again, you have this code from last week, so up to you if you want to mess with that. You can also do this in the initialization list style if you want. The destructor, all it really has to do is call the clear function. Get size is low-hanging fruit. Now the other thing to remember here is that we're in the public section of this tree, and most of the public functions, not all of them, but most of them, their job really is to call one of the private functions starting at the root pointer. So the job of the clearing function is really to launch the clearing process at the root node. So it's going to call the private version of the function. And the way C++ can tell the public and the private one apart, by the way, is that the public one takes no arguments and the private one requires a node pointer argument. So if we go down to the private one, a clear, C++ can tell them apart because this one requires that you put a node pointer in it, whereas the public one does not. So C++ can use that when it sees a function call to figure out which is which. But really most of the public functions, their job is to just make sure that the private function gets launched at root. So clear is going to do that, insert's going to do that, so we're really just going to call the private version of this one. We'll pass the piece of data along and then start the actual algorithm at root. And if I scroll down to the private insert function, C++ knows that that one's different because that's the one that takes some data and a pointer to a node. So that's what the public one does, is just launches the process at that spot. Oh, I made a mistake, so let's be careful here. When it's void, then you just call the private one. When it is supposed to return something, then what you have to do is kind of, I think of this as like a bucket brigade. So please insert, and then I'll pass back what you did. So the public insert function has to return the result that it gets from the private insert function. So be on the lookout for void or not void to make sure that you're doing returns where you have to. I noticed that because I noticed that find returns a bool, which means what I really need to do is return the result of launching the private find function at root. And if I go down to the private find function, it's the one that takes a target and a pointer to a node. Remove is going to be the same thing. So we just the public function is not going to do the removal. It's simply going to return the result of launching the private remove function with the given target, starting at the root. It's always going to start at the root, although technically it doesn't have to. It could start at the root's left child if it wanted to, or the root's right child, but it's pretty much always going to start at the root. Let's see here. So same thing. There's probably, I'll check for a private remove, and I'm sure there's a private get. So here's the private remove. It's in the private section under this label here. So the private remove is simply pass the target with the node get. So there's a private get. So we'll simply return the result of doing the private get on that target starting at the root. Print in order. There's a private print in order, I'm sure there is. So this one's void, so I don't have anything to return, so I will just call the private one starting at the root. I know that I should start at a node because if I look at the private print in order, it says tell me where to start. What node should I treat as the root? Which typically you're just going to say, well, the root. Same thing here, print reverse order. There's a private one, so the public one, all it has to do, it's void, so no return. All it has to do, I forgot the arrow up here. all it's got to do is get to the private one. Be careful you're getting to the private reverse order, in order, reverse order, starting at the root. So the public functions really have almost no work to do. They just make sure that the correct... I did. Yeah, you caught it. So you're correct, Jordan. I left that off, and that was a mistake. So good catch. Okay, so notice that here's the private section below, so all the public ones, all they do is make sure that the control of the program gets down into a, um, no, it's good to watch, because it was just sheer luck that I noticed that, so I need you guys to help me with that, so that's great. I very much appreciate it. Okay, so anyway, that's all I did with the public functions, is make sure that we get to the private functions and let them do the work. And the thing to remember is, if I'm returning something other than void, be careful that there's a return statement there. So just constantly look for that. Is it void or is it not void? Okay, the node's already been done, so that's good. All right, so some of these are going to be the same old stuff. So these are the actual working functions. These are the ones that actually have to do the work. And generally the model is, if you've given me a place to work in the tree, which is what troot is, where in the tree am I? If that's not null, then we're safe to do something. So very often that's going to be the check. If that root that I'm working on right now is not null, then it's safe to do stuff. In this case, I need to be deleting nodes. So we did this one last week, but basically if you're going to clear out, I do have a drawing, don't I? Yeah. So if you're going to delete a node, so if this is troot, basically you want to make sure that the left child and the right child get cleaned up first. So you clean up the left child or the right child, but clean up the left one, clean up the right one, and then clean up the root. And we don't actually have to do that work, we'll just make recursion do that work. This is a void returning function, so all I have to do is clear. So I'll just send the function down the left to do whatever clearing does there. Then I will send the function down the right. And then I can clean up the actual node that's the center of this tree, so I'll delete it. And it's not bad practice, I didn't do it last week, but let's make it null after we delete it. That's the whole function. Recursion takes care of the rest, right? These calls down the left just ensure that whatever has to happen down there happens. But I did kind of a long walkthrough of that one last time, so if you didn't see that, that one's still out there from last week. I believe I did clear on Thursday. Okay, so there's the clear. Insert is a little bit different. We did this one last week as well, but I'm re-implementing it. So what insert's looking to do is, in this case, on an insert, if you have given me a null place to work, that's a place to put a node. So in the case of insert, I want that to happen. So I want to find null because that's a place where I can now put a node on insert. So on insert, I'm looking for a blank spot to put a node. The other thing to be careful of here is that if I'm going to recurse on this one, it has a return value, so I need to watch out for that. But if you've given me basically an empty branch of the tree, well, I can use that empty branch to make a new node. So I'll just make a new node with that new data and then connect it right to that branch that you gave me, this branch. And I'll increase the size and I will return true because I succeeded. Now I have to handle all of the other possibilities. So if we use this top tree, um, if you're asking me to insert something, let's just say you tell me that you want me to insert 8. Then since you're going to start me here, well, that's not going to be null. That's not an empty branch. So I need to use recursion to get to the correct section of the tree where I hope to find an empty branch. So we look at the data we have. That's the parameter. If that is less than, is it called data? What's it called? Data. So if it's less than the node's data, so 8 is less than troot's data, which is 10, then I need to go left with recursion, and I'm going to fix this, so just pay attention to this part. Same data, I haven't inserted it yet, but I need to reset the whole insertion process down to the left. Now this is the thing that to watch out for. This is very important. This function I just made a recursive call to a function that returns something other than void. And if I do that, then I need to make sure that I return from that recursive call. So that return is there on the recursive call because the function, when it's called recursively, is going to return some data. So if the data I'm trying to insert should come to the left of where I'm looking at right now, then I will reset the whole process going down to the left one step. It's also possible that the data coming in should go to the right. So recursive call, I will return what happens when I try to insert to the right. And there's one other possibility. The one other possibility, insert. The one other possibility is I'm trying to insert a duplicate. So something that's not less than and not greater than. And in our tree, we're not going to allow duplicates, so we're going to return false on that and just reject the duplicate data with a false. So that's also one that we did last week. So I just rewrote those and sort of talked them through without drawing pictures this time. At least it's not as many pictures. That takes a lot of turning over in your head for a while until you get comfortable with that. So you do your best to draw pictures, and for a while the pictures aren't going to work quite right, and they may not even make sense, but you will get there if you keep hammering away at it. This is a very powerful way to solve problems with recursion. So if you can get it straight in your head at some point, and it just takes work, you'll be glad that you did, because it's a powerful programming tool, or algorithmic tool, recursion. Okay, so there's that. Just going to keep going. Okay, a find. So let me draw a new tree. And put some data in it. I'm going to put a 50 here this time to give myself kind of more space, and a 25 and a 75. Let's just start with a real basic one. So the idea of a find is that we're looking to see if we can find a particular piece of data anywhere in a tree starting at some root node. We will return true if we can find it and false if we can't. Okay, so let's let's deal with the null first. So one thing I'll just sort of say to you that you should carry around in your head is try to deal with the null pointer first. So when you're developing an algorithm, imagine what you would do first if you come into an empty tree. So let's say, for example, what can you? I lost my view of my drawing. Okay, so I'm just going to draw it over here to the side. If this, no, what I'll do is I'll pull this up and then I'll push it back down. So let's say we're trying to find data in an empty tree. Let's just say they want to find the value 5 in here. Um, it's going to fail. And it's going to fail immediately on this null pointer. Null pointer says that there's nothing in there. So you should deal with the null first. So let's deal with the null first. If troot, this pointer, is null, well, it's not there. Um, that's a false. I failed to find it. You're going to see something familiar here in just a second. So I have the insert algorithm sitting up on top of the screen. So just keep that in mind. Let's see how this one kind of mirrors it. Okay, but what you're going to watch me do, well, in the case of insert, when we get to a null, that was good. On find, when we get to a null, that's bad. But let's handle all the other possible stuff. So we dealt with null first up here, and then we said, what if what I'm looking for should be at the left? So let's do that. If the target I'm looking for comes before, in other words, is less than the data at that node, then I need to go to the left to look for it. So I'll look for the target, but instead I'll go down to the left. And I did this again on purpose. This is a recursive call to a function that returns a value. So I need to be very careful on the recursive call that I return the result of descending the tree. So for example, on this tree down here, if I were to do a find on 25, starting at root, well, it's not going to be null, but it's going to be less than that 25. So I need to go to the left, is all I've done here. Another possibility, let's say it's 125. Another possibility is that what I'm looking for, the target data, is greater than the data at that node. Notice that this mirrors very closely the insert function. What if it's null? What if I should go left? What if I should go right? What if I'm dead on it? So if I should go to the right, then I should return, because I'm going to recurse, return the result of having gone to look for that target to the right. The other possibility is that I land on the data. That's the else part. So in the case of insert, if I land on the data, I refuse to insert it. I return false because I'm not going to insert a duplicate. But in the case of find, if I land on the data, that's actually a successful search, is it not? So if you notice though, it's the same checks. Am I looking at a null? What do I do? Should I go left? Should I go right? What if I'm dead on it? What should I do? Okay, we're going to stub out some functions here. We're going to save remove for Thursday. This is by far the most difficult thing to do in a binary search tree. This one um, has some counterintuitive pieces to it. So for now, we're going to stub it out, and that means to stub out a bool, I'm just going to return something. I'll say false. I'll fail some tests because of that. I'll pass others. Um, that's a void returning function, so to stub it out, I can just leave it be. This one returns a pointer. That pointer, by the way, can be anywhere. People have asked about that. So I'm actually returning a pointer to whatever a t is, so I'll just, to stub it out, return null. This one's a void. This one's a void. So I'm going to go just get a compile on it and see if it's okay. And if possible, if it'll compile, then I'm going to run the test. Let me get my camera off. Sorry. I didn't have a catch file in here. Okay, built. I'm going to run it with the -s option like I always do, just to see the details. So I'm passing 9, I'm failing 2. I expected to fail some because I haven't even implemented them all, but somehow by some kind of magic I'm passing some. So isn't that, oh, there's a crash at the end. So it didn't actually run past line 55 of the test. It failed that one, and then whatever happened next caused it to crash. That's to be expected because I have not implemented all the functions yet. Okay, but we want to make sure and compile. So we compiled, it did compile, it ran part of the test before crashing. That crash is probably due to a bad pointer value somewhere, like a null pointer. But that's fine. Let's keep going. Remove, we're skipping for now, and that could cause crashing behaviors. But let's work on get, and then we'll work on print in order and print reverse order, and then we should be done. So watch the pattern of get. So what get's supposed to do is return a pointer to a piece of data. And the reason why you would do that is because someone can use the pointer to alter a piece of data. So this is being nice to other programmers, that you will let them have a pointer into data in your tree, and then they can use that pointer to interact with that data in your tree. They can't affect your tree really, but they can use a pointer to a piece of data to go inside of a specific node and interact with a piece of data inside of a node. But you're going to watch me do the same thing. So the only difference between a find and a get is that a find returns true on a success and false on a failure. A get's going to return null on a failure and a pointer on a success. So, but it's the same setup. If at any point in my algorithm I fall off the tree, then whatever it is I wanted to get obviously wasn't there, so I'll return a null pointer. Kind of the same as the find. I'm trying to use recursion to force the algorithm to descend to the right section of the tree at any given moment, looking for a target. But if I get onto an empty branch somehow in the process of trying to get some data, that's bad, so I'll just immediately return null pointer. It's possible that the target I'm looking for is less than the data I'm looking at, in which case this is a returning function, so to recurse to it, I'm going to return the result of trying that get, but instead down the left. But do you notice it's the same checks? If the root's null, if the target's less, if the target's greater. Recursive call on a non-void function means I need to do a return on the recursive call. So I'm getting the same target, but I'm going to try to go down the right and see if I can find it there instead. The last one is I found it. I found it. So what they really want is the data, except for that's not precisely what they want, because they want a pointer to the data. Not the data itself, but a pointer to it. And the way you turn that data into a pointer, I'm going to wrap it in parentheses just to be on the safe side, is you put an ampersand in front of it. Now you are giving them not the value of the data itself, but an indirect reference to it, a pointer to it. And they can use that pointer then to view the data, to alter the data, that kind of stuff. But notice that the algorithm is mostly the same. Did I land on an empty branch? Do something different. Should I go to the left? Then recurse to the left. Should I go to the right? Recurse to the right. Or I landed exactly dead on what I was looking for, and then what do I do? So I'm going to go back and, did I bring it? Okay, so I'm going to go build that again. I'm going to make a lab15.exe file. And then I'm going to run it with the -s option so I can see all the details. So the last time I passed 9, failed 2, and then crashed. Way better this time, by the way. I didn't even crash. So whatever was causing it to crash was related to that get that I just wrote. I'm still failing some, but that's to be expected because I haven't finished everything. Okay. Remember, we're skipping the remove until Thursday because those are hard, and I'll walk us through those next time. It'll require some picture taking, drawing, not taking. Okay, last two. Print in order, we've done. So sometimes it's just a matter of, in terms of printing, let's just make sure that we don't try to do anything if we fall off on an empty branch. So we're just going to make sure that that pointer is not null. If it's not null, then it's safe to do stuff. To print in order, we talked about this last week, but to print in order, like on this one, so in order would be 25, 50, 75. So I'm going to use recursion to pick up the 25, and then I'm going to print the 50, the one that I'm looking at, and then I'm going to use recursion to pick up the 75. And like we walked through last week, there's a magic to it. If you get a bigger tree, if you trace the steps that the functions have to go through, you will find that somehow magically it works, which I recommend that you try to do. But it will work if you trust in recursion. So the whole trick is to use recursion to pick up the left, print the center, and then use recursion to pick up the right. And it just works. Just don't let nulls get in the way. So I'm going to use recursion to pick up the left. I'm going to print out the data for the node that I'm on. I think I'm supposed to put end lines in here. I can't remember. And then I'll use recursion to pick up the right. And you just have to, at first, trust that this works. And you don't entirely have to trust it, because you can write tests and you can see that in fact it's true, it works. But it's really just a matter of use recursion to get the left to print, then print the node that I'm on, and then use recursion to get the stuff to the right. I'm going to go ahead and compile that and run it before I do print reverse order. But while I'm doing that, I have a go at this. Just see if you can implement print reverse order. No one's going to see you do it. But if you think you've got it and you have the courage to share, then print your copy and paste your print reverse order into chat. So I'm going to sort of just dawdle for a couple of minutes. I'm just going to compile what I have, and then I'll wait for a minute or two and see if anyone wants me to try their code for print reverse order. So compiling and testing my print in order to see if I pass any more tests. I think I was passing 27. Still passing 27. It should have been different, at least in theory. Oh, some of them are going to fail because we haven't done remove yet. That's true. That's true. We're still going to fail some because of remove. That's alright. There's one that passed. And it's not crashing, so that's good. 58 assertions, 27 passed, 31 failed. It's okay. So I use chat there just because the chat is not have a little delay on it. But if you wrote a print reverse order and you want me to try it out, I will. If not, it's okay. We'll do that one too. Okay. Um, I'll go ahead and do it. Looks like I've lost some viewers anyway, so. But if you're going to watch the video later, then print reverse order is simply, I need the, why is that not working? Okay, it is. Print reverse order is simply I need 75 followed by 50 followed by 25. So print reverse order is just descending order, bigger numbers descending down in order. And the way to do that is to use recursion to get everything to the right, then print the node, the root, and then recursion to get everything to the left. It's literally just the reverse of in order. So I will use recursion to get everything to the right this time. And then I will print out the node that I'm on, just like I did with in order, and then I will use recursion to get everything to the left. So it's right, center, left to print reverse order as opposed to left, center, right for in order. And then I'm going to go compile that just to make sure it works. Oh, maybe that's the problem that some people are having. Hopefully the video's intact, but if you think you missed something, though, please let me know in chat. For me, I passed a 28. I was only passing 27 before. So after doing print reverse order, I now pass 28. Um, I am still failing a whole bunch, and that's probably because I haven't done remove, and I'm not going to do remove today. I'm going to do that on Thursday. That one's hard, and I want to not be tired and be able to draw lots of pictures. So, um, and plus that's a lot of code for you guys to look at in one day also. Okay, so what I'm about to do is take a break and go get myself some water. And when I come back, I'm going to give you some ideas about um, how to maybe get slightly better results. I mean, everyone did okay on the third project, but probably many of you would like to do slightly better. So I'm going to try to give you some ideas about uh, doing that. Okay, thanks, Jack. And sorry that I mean, obviously none of us controls Twitch, but sorry that that's going to be a pain in your rear end. Okay, so I'm going to take a break. When I come back, I'm going to give you some ideas for Project 4 so that we can um, still crashing. So I'll leave my code up while I take a break. Um, Let me put it on. So there's the last three things that I did, or those things. So I'm going to just highlight the last few things that I did. And for me, Jordan, when mine was crashing until I got the T star get function working. So hopefully for you, that's what'll get you past that crashing spot. So I'm going to take a break, but I'm going to leave this code up, and then when I come back, I'll do some Project 4 ideas. So anyway, give me a sec. All right. Sorry about that. Thanks for waiting. But I also thought sometimes you could use just a little bit of a moment to breathe in between these segments. Okay, so I wanted to help you get started on Project 4. Now, there's some things that I just kind of hope that you have, and I'm happy to answer questions about these features, but I've already written my file loading code because I just want to get right to the point of it. Um, so I'm happy to come back here after this next segment, and also again, Wednesday mornings are usually I'm completely alone or one or two people around asking me questions. So I have my file reading. It's the same one. Um, Open up a file, load its contents one line at a time into a vector, um, and I pass the vector by reference, and I return true or false. Anyway, um, yours should have an int argc and a charg star argv, but I'm not going to program for that because I want to save time. So um, I'm going to make myself a text file called input1.txt. Um, that line should ultimately be replaced by the real logic of the program, which will use argc and argv and get the file name and all that stuff. So I'm not doing any of that. I'm just going to sort of assume I have an input1.txt. I'm going to make a file called input1.txt. So input1.txt, which I don't know if that shows up on your thing, does it? No, it doesn't. So once I save it, I will show you that it is called input1.txt. If I open up, so the files that I have, let me get rid of this. I'll get rid of this too. Alright, so here's what I have in my folder. I have my tree code from the lab. I have this catch code from the lab. I have the lab from the lab. Well, but what's important is that I have the tree and a driver and my own input file. So instead of just relying on the sample input and crossing my fingers that any other input's going to work, I'm actually going to make my own input file using the project for requirements. Right now it's completely empty, by the way, and that should not cause a problem, so I'm going to prove that here in a second. So anyway, I did all that so you kind of know where I'm at. The other thing I'm going to need up here in my driver is I'm going to need to include bstree.hpp because I need the data structure. And again, I'm hard coding the file name in. Do not do this on the project. You'll lose a decent chunk of points for it because you won't be adhering to the requirement, and you'll make our job of testing it more difficult. I'm just doing this because it's way faster than all this other stuff, and I'm not finishing the project today. I'm just doing some testing. Okay, so I need to make myself a vector string file contents. I'm going to call it commands. No, I'm going to call it just contents. Okay, and then I'm going to say if read file, file name, that's my local variable, and then I'll pass in the contents. If that comes back true, then all was good. In theory, you all already know this part, but I just don't want to have dangling incomplete logic. So if I call read file like this, and it comes back true, I should have the contents with stuff in it, right? And then I can simply just cycle through all the contents. I'll call each of them a command and work with that. The other thing I'm going to need in main, just like last time, is I'm going to need a binary search tree. And what kind of data are we using on project 4? Browser, where's that go? What kind of data is in project 4? I'm going to look at the operations. Well, let's just look at the input file. Okay, it's strings. So it was integers last time, but what I'm inserting in the tree now is strings. So my binary search tree is going to be of strings. I know, like last time, well, I do because I went and looked at the project plus I wrote it, but it's going to be the same setup. where you're going to create and delete and recreate and delete and clear and insert stuff and remove stuff and all the things that a tree can do. Um, all right, so this is already getting a little bit complicated to look at, but that's my data structure. And what I'm instructed to do in the project is start off with no data structure. So there's no tree, it's just a null pointer that I can use to make a tree. Then I have hard-coded a file name, which is a bad idea, but I wanted to show you. It's a bad idea. Well, it's not a bad idea. I'm just saying that's not what the project's supposed to do. So I'm worried that me putting it in here means that other people are going to do this and say, but you showed it on the video. This is not how it's supposed to be for the project. Hopefully that gets the point across. That's just because that's faster and it's less crap for you to look at. So I get my contents and then I'm going to cycle through them, and then just like before, I'm going to switch on the first character of each one of the commands in the file. If I go look at the project again, and I look at the operations, it's a lot less. So a lot less stuff than a doubly linked list can do. So that is a huge relief. That's all the more I have to deal with. And then the outputs are going to be very similar. Tree cleared, tree deleted, tree cleared. Probably there's something about tree, oh yeah, like tree empty. Must create tree instance. So all this stuff should be familiar, so I'm kind of just leveraging your same experience from the last lab. But what I wanted to show you is you don't need, you should be using the input files and creating your own input files to test those parts of your program that you think you're ready to test. So let's just do a super basic one, like clearing. Not clearing, creating. Let's just do a create. So what would that look like? Well, in my input file, the command looks like this. That's it. So I can make my own input file that only creates a tree. And then I can totally anticipate what I should expect to have happen. It should also, by the way, handle comments. So I can even put 2 comments. You should make them, and you should share them with each other. You can help each other out. But I could just build this out. So I'm just going to handle that much. So case C, and I'm writing the commands in the file for myself, and then I can sort of control what happens next. Case C, just like before. So C. If an instance already exists, delete it before creating a new one. So we did this one before. If my tree is not presently null, then I need to get rid of it with delete. That's it. And then create a new one. And then print out a message. Tree created. And I can do that. And in fact, if I want, I can do this a whole bunch of times just to see what happens. I can see if it crashes. I can see if it should do 1, 2, 3, 4, 5 tree createds. Oh, I need to go compile it. So let me go fix so you can see me compile it. Browser off. So what I'm mean to be showing you here is that you don't need to rely entirely on the sample input file. In fact, you shouldn't. You should create your own input files and put sequences of commands in them that test out the different capabilities of your tree. And I'll show you one example here after I build once before I quit. So now I need to g++ driver.cpp. Oh yeah, I'm writing Go code, I guess, because I didn't put parentheses around that thing there. I forgot the parentheses around command at 0. Okay, so now if I run the program, it's going to load up my input1 file, and it's going to run 5 creates that I put in my own file. 2, 3, 4, 5, that seems all good. And then we can do some other things. So I'll just do 2 quick little tests. Let's see, what's another command we can toy around with? A deleted. Now deleted is one that if you, any operation other than create that comes in with a null pointer should say must create tree instance. So what's deleted? Is that a D? It's a D. Deletes a D, so I could put my case D in here. If I have no tree, else I will delete it and set it equal to null. So now I can test this, right? Because if I go to my input file and I put a delete at the very first, it should say must create list instance because I have tried to delete before I ever created one. And then if I do one at the very end, it shouldn't say that. What should it say? Tree deleted. It should say tree deleted at the end. So the first one should say must create. The last one should say tree deleted, except for I didn't put the output there. So my guess is that a lot of people didn't think to do this. That, oh, it's just a text file. I could actually do whatever I want and make my own. So if you didn't think to do that, then now you know. So there's the must create, like I hoped, and it did. And then there's the tree deleted because there was one at that point that could be deleted. So my own little test. I can even do a get test at this point based on the lab work that we've done. Where's the get? Oh, here's a find. So not found, tree empty. I also have to do the, why tree empty? Well, because it says. So there's more complex logic here for this one. But let's do an F. I forgot to put a break down here after D. Alright, so an F. So if the tree is null at this point, that's a problem. Now this one says I should print out when the tree is empty, so feels to me like I should say that next. So if the size of the tree is 0, then I'm supposed to say tree empty. Otherwise, I'm supposed to let the tree go do a find. So the find returns a bool. I will show you where the find returns a bool. So it's going to return true if it found it, false if it doesn't. So bool result equals tree find. Oh, I got to get the data here, which is going to be a remember that code we wrote last time about that? That function that I wrote for you for the last lab. I don't have it here, but I'm going to have to fake it. And then if result equals true, Actually, we should do that in steps. That's not a get integer, by the way. I can just skip the first two characters because it's strings and just go straight to the substring. So that makes life super easy. Um, anyway, just the point here, though, I'm doing my little, oops, making my own little F test. So if I do, then I will say cout. That substring was found. Otherwise, so it gets a little bit more complicated. You just sort of have to stop on each thing. But if you're doing it this way, then you can just focus on the one command. Unless you wait and you have to rush, then it's a lot more stressful. What else? Found W or W not found. So found goes on the other side. Found that substring. Otherwise, that substring was not found. And then I can go do my own find. So I go back to my input file. I will put a find in here somewhere. Why not just right after the first one? My code also handles empty lines. My file loading code. So I can try to find something. Should say apple not found because it won't. But the point here again is that the sample input file is a sample input file, which means we use others. So I craft these to test your code, and you totally have the power to craft your own and test your code. So I did change the code. I have to compile again. Oh, yeah, the tree's empty. That's what I would have expected, right? Um, I would have to put something in the tree to try to find it later. So anyway, you get the point, I hope. You can make your own input files, and then you can make a whole bunch of different ones. You can make input files and share them with your classmates. What you're trying to do is put together sequences of commands that expose bugs. So when I am making input files after you submitted your projects, I'm trying to put together sequences of commands that expose bugs. So I'm trying to insert duplicates, I'm trying to find non-existent things, I'm trying to find on null trees, I'm trying to do all that stuff to expose bugs. So take advantage of the fact that this is just a text file and you can create as many of them as you want, um, and expose your own bugs and sort of look for issues that way. Plus you can share them with each other. Okay, so that's a pretty good run. That's an hour and 5 minutes roughly, so I'm going to stop. I'll wait for questions. If you want me to leave a piece of code up for a bit, I'm happy to put it back. In fact, I'll put it back on the driver. Can't really show all of it. It's the same driver except for a different data structure and different commands. Okay, so have a good rest of your day. I will be here at 10 tomorrow. I'm happy to answer questions. I'm usually alone for an hour at 10 on Wednesday mornings. And then if I don't see you then, I'll see you again on Thursday at 11 a.m. You too, Jordan. See you Thursday. Have a good day. You too, Jack. Thanks. Sorry there was hiccups in the Twitch. Hopefully the video has all the bits and pieces you need, but email me if it doesn't, and I'm happy to answer questions.